Hello, everyone. This is the lecture 13. We're keeping going with the correlation analysis, and I made an introduction last week, and I gave you some example, and we studied some calculation for the correlation analysis, especially for the Pearson correlation coefficient. We missed something last week. We haven't really studied the testing the correlation. The calculation is okay, straightforward, but it doesn't mean any calculation you're making is going to be significant. So you need to check whether the correlation coefficient is significant. The null hypothesis you construct for the correlation coefficient is the null is always rho equals rho null, and the alternative hypothesis is rho either for left-sided rho less rho null, or let's construct another one right-sided. So you may construct for the rho is the population correlation coefficient, and rho null is always fixed, and this is for the right-sided. The alternative, rho is greater than rho null. So the other one more we have, and the double-sided HO, rho equals rho null, and the alternative, rho is not equal to rho null. And so I call this left-sided, and that one is right-sided, and that one is double-sided. Okay. To test such hypothesis, we use the following statistics, and this statistics actually, and we use to test such hypothesis. We use the following statistics. So this is the statistics. T calculation equals R. This is from the Pearson. So you may have a subscript as P, but I don't see this subscript in the literature, so I will skip. I will have only the sample correlation R minus rho null, and that's divided by the square root. Within the square root we have 1 minus r square divided by n minus 2. Another thing is there is a degree of freedom for this calculation. To make up your mind whether the hypothesis constructed is significant or not, you need to get the critical value. So for the critical value, we use a degree of freedom. That's the degree of freedom is n minus 2. And n is the sample size. That's the sample size. Okay. Here you go. Let's have a quick example Okay, let's get a quick one. Example. Um, test that. Test that. Test that whether the the null hypothesis is significant for the given statistics result. Okay, so let's say the null hypothesis is rho equals 0.75, and the alternative, let's say rho is less than 0.75, and the given statistics is the Pearson correlation. Let's say this is calculated as 0.69. It seems that 0.69 is less than 0.75, but we're not sure really whether this statistics is significantly less than 0.75. So this is the given sample correlation, the Pearson correlation, and let's say the sample size is say 23, let's say 23. Okay, nothing left to test the statistics. So the t-calculated statistics, see that this is the t-calculated statistics. And so rho null, in this case, rho null is 0.75. The calculated statistics, so I'm going to copy this formula here, have it downward right here. Okay, this is the calculated statistics, so I'm gonna substitute everything in here. Okay, equals 0.69 minus 0.75. Okay, and that's divided within the square root. Okay, 1 minus 0.69 square divided by 23 minus 2. Okay, the calculated statistic. Let's see the result. Let me get this calculation done. Okay, can I get it using my calculator? 0.69 minus 0.75 divided within the square root. 1 minus 0.69 square divided by 23 minus 2, and the result is minus 0.38, minus 0.38. Okay, since this is a left-sided hypothesis, the critical value should be obtained from the degree of freedom 21. The degree of freedom for this example is 21, and the critical value equals T21. And since the alpha level is not given in here, you may use the universal alpha level, which is 0.05. One thing, let me get back this, the critical value, since this is a left-sided, it will have a a negative sign. So this is going to be minus T21 0.05. Okay, let's get this value from the T table. I should have this table from the previous lecture. I'm gonna go very quick to get it, maybe right here. So those are the F table, and this is the T table, I guess. Yes. No, this is the standard normal distribution table. Let me get the T table. Yes, that's the T table. Okay, this see that 21 is the row I need to consider. This is the degree of freedom from 21, and I need to use the 0.05, the column 0.05. So my my critical value will be for 0.05 and 21 degree of freedom. This is the intersection 1.721, and I also have a negative sign. So I'm gonna go back to my lecture notes, type this, the value in here. So this is minus 1.721. That's the critical value. So if you draw a picture of the critical region for the T statistics, so I'm gonna draw it right here. Okay, let's shorten this one. Yeah, shorten it. Yes, that's it. Okay, since this is a left-sided, I'm gonna have the critical value here, right here. Okay, minus 1.721, and that's the accept region, and that's the reject region, reject area, 0.05, and that's 0.95. Okay, and highlight this part. Okay, that's the critical region. All right. Yeah, that's it. Perfect. Okay. The calculated statistics is minus 0.38, is simply falling within the accept region. So it could be somewhere here. Let me draw a different color. Okay, simply it will be falling. This is okay, and that's minus 0.38 is within the accept region. So in this case, I will not be able to reject the null hypothesis. Okay, since let me write it to the right side, the space, since minus 0.38 is not less than minus 1.721. This is not less. Then we do not reject the null hypothesis. Okay. One thing more for the testing, if you have the ability to test statistics and you're able to construct a confidence interval. Okay, the next thing is confidence interval, confidence interval for Pearson sample correlation, let's say, or sample correlation. Okay, the confidence interval, let's use different color this time. For 1 minus alpha times 100% confidence interval of Pearson correlation may be constructed as follows. Yes. So you have the sample correlation R is you minus the critical value. For the confidence interval, we always use the double-sided critical value, so you split the alpha level into half, so the critical value T, the degree of freedom doesn't change, n minus 2, and the alpha level is divided by 2, and that's multiplied by the standard error of the Pearson correlation, which is 1 minus r squared divided by n minus 2. That's the lower bound for the confidence interval for the population correlation coefficient. And this is the lower bound, and the upper bound, the only difference is I have the negative sign in here. That negative sign is going to be positive in this side. Let me copy the lower bound to this side. Okay, the only difference is I'm gonna make this negative sign to be positive. So that's the difference. This confidence interval can make you confused because the lower bound can be sometimes less than -1, and the upper bound can be greater than 1 sometimes. But in this case, you need to, if you get the lower bound less than -1 and try to have the lower bound to be -1, change it to -1. And if you somehow find the upper bound to be greater than +1, and just try to truncate the upper bound to be 1, because the correlation coefficient can never exceed +1 or can never be less than -1. So this is This is the thing you need to be careful in the construction of the confidence interval for the correlation coefficient. In many um, in many in many books they don't care about the this stuff, and in many statistics software you may get a lower bound less than -1 and greater than 1 for the upper bound, but this doesn't mean to be true, and those type of software doesn't care about the lower bound. They just present you the calculation. You can't just consider the calculation to have less than -1 correlation and greater than 1 correlation, so be careful about this. Let's have an example to clarify this. An example. Okay. Okay. Um, for the given statistic result, construct the confidence interval for the population correlation by 95%. Okay, let me give you some stuff for the given statistic result, and the Pearson correlation. Let's say the Pearson correlation coefficient is given to be 0. Say 91, and the sample size, let's say, is given to be 42. And what else you need? Yes, that's it. That's all you need. Let's see what the lower bound is and what the upper bound is. Okay. So if you substitute within the confidence interval, R is 0.91 minus, so you need to okay, before we start to construct the confidence interval, let's get the t n minus 2 alpha divided by 2, and which is t. 42 minus 2 becomes 40, and the alpha level, so since this is 95%, 1 minus alpha times 100 is 95, and from there we get the alpha level to be 0.05. Okay, so since the alpha level is 0.05, alpha divided by 2 becomes 0.025, and I need to go back very quickly to the t table from the previous lectures. I'm getting close to the t table. This is the standard normal distribution table, and you all have this table, I guess. I need to look for the degree of freedom, 40, and that's the degree of freedom, and I need to get the 0.025. This is the green line. This is for the alpha divided by 2, so I need to, okay, so 0.40, and this is the critical value 2.021 from the t table, student distribution t table. Okay, let me shorten this. Okay, 2.021. So I'm gonna go back to my lecture today and have consider the critical value to be 2.021. So in this case, this is 2.021. All right. Okay, let's construct the confidence interval. So R is 0.91 minus 2.021 times 1 minus 2.021. Sorry, this has become the Pearson correlation coefficient, which is going to be 0.91 square divided by 42 minus 2. Okay, this is less rho less 0.91 plus 2.021 times 1 minus 0.91 square divided by 42 minus 2. Let's see, we will have a surprising result, I guess. I'm expecting the lower bound to be a surprising result. Let me get the lower bound first. Calculate the lower bound. 2.021 times 1 minus 0.91 square divided by 42 minus 2. Okay, the lower bound is 0.7775. Okay, let's roll. Let's see the upper bound. The upper bound is, as I said, I was expecting this surprising result, 1.042, which is in practice the correlation coefficient can never exceed 1. That's not possible. That's not possible. So in this case, you need to modify this. So the lower bound is okay, 0.77775. Let's roll. So you can get at most 1, the correlation coefficient. So you can also have equality for the confidence interval. I'm gonna have an equality because the Pearson correlation can get the value 1 and can get the minus 1. If you are given a confidence interval and also given a hypothesis, double-sided hypothesis, you can easily use this type of confidence interval to test such hypothesis. The above confidence interval can be used to test the following hypothesis. So if you're given to be HO rho equals null, and the alternative row is not equal to null. And say alpha is 0.05. In this case, we check whether the confidence interval is including the zero value. In our example, okay, one thing more, zero value to accept the null hypothesis. Okay. In our example, since the lower bound is positive and the upper bound is also positive, so the null hypothesis is rejected with alpha equal 0.05 level of significance. Okay, and that's it. And now I think you're clarified how to construct a confidence interval for the Pearson correlation. And there is another correlation coefficient. It is mostly used in statistic literature, in business statistics as well. It's called the Spearman rank correlation. The Spearman rank correlation. Okay. All right. The difference between Spearman rank correlation and the Pearson correlation coefficient is the Pearson is considering the bivariate data set should have a normal distribution. In contrast to Spearman rank correlation, the data set should be continuous. X and Y, the measurements should be continuous and having a normal distribution, Gauss distribution shape, bell-shaped distribution. And the Spearman is only requiring the data set to have ordinal, at least ordinal. You could have continuous data as well. The only difference is you don't need to require the normal distribution for the data set. That's the difference between Spearman and the Pearson. Of course, the Pearson correlation is more powerful than the Spearman because it is parametric statistics, and the Spearman is also called non-parametric statistics. Um, the definition actually, you may write this for the definition for the rank correlation. When examining ordinal data, when examining ordinal data, consisting of two sets of rankings, the resulting correlation correlation coefficient is referred to as Spearman's rank correlation, as Spearman rank correlation. And this is denoted as R with subscript S. This is to distinguish between the Pearson correlation, and I didn't prefer to have a subscript for the Pearson because you don't observe this type of subscript in the literature. In any books you don't have a P subscript letter, but you could observe for the Spearman rank correlation to have a subscript S. This is the S standing for the Spearman. Okay. The value of the Spearman is always between the value of RS is always between -1 and +1. It is sometimes desirable to analyze the relationship between two variables according to the rank values of each of the variables in the sample. So the variables may be ranked on the basis of quality, let's say televisions, as the televisions were, or any other standard. The use of ranks allow us to measure correlation using characteristics that cannot be expressed quantitatively, but that lend themselves to being ranked. For instance, it is difficult to measure the quality of a television picture quantitatively. Let's have an example. Let me give you this example. I have an example from a book. I also followed last week lecture. I prepared my lecture note from this book last week. Let's have an example. Okay. Mr. Roberts, and Mr. Clausen, each examine 8 different brands of television sets and rank them from 1 to 8. Determine the sample correlation between these two sets of rankings. Two sets of rankings. The brands okay. Roberts X and Clausen Y is Y. Okay. We have 8 different brands calling A, B, C, D, E, F, G, and H. And the ranking by Roberts, Mr. Roberts, is 1. For brand A is 1. For brand B, he gives 4. And for brand C, he gives 2. And I keep going 6, 8, 3, 7, and 5. For Mr. Clausen, in contrast to Roberts, he give a rank for A, brand A is 2 in place of 1, so it's different, and 3 for B, 1 for C, and 6, 7, 5, 8, and 4. Okay, those are the ranking. It doesn't make any difference to calculate the Pearson correlation and the ranking correlation, the Spearman's ranking correlations. I'll tell you why. It is very surprising. It will be very surprising for this example. So let's get the calculation for using the way of the Pearson correlation. So you need to have x and y, the calculation of x and y. xy, and you need to have xi, yi, let's say, have a subscript, okay, and you need to have xi square, you need also to have yi square, okay, x and y, 1 times 2 becomes 2, 4 times 3 becomes 12, 2, 36, 56, 15, 56, and 20. And xi square, 1, 16, 4, 36, 64, 9, this is 64, 64, 9, 49, and 25. And this is 4, 9, 1, 36, 49, 25, 64, and 60. Okay, so if you get the summation for each of these columns, okay, the sum of x is going to be 36. The sum of y is also 36. Summation from 1 to 8 becomes always 36. The cross product multiplication xi, the sum of xi and yi, if you adding up all this value in here, you will get the result to be 199. And the sum of xi squared, adding up all these numbers, you get 204, and this is also 204. Okay, nothing else missing, and it is going to be easy for the calculation of the Pearson correlation coefficient, or Spearman. You can also call it Spearman because the data set itself is not a continuous data set, but the calculation way is the same. So I'm going to use the Pearson correlation coefficient. Remember this coefficient from the past week lecture. Let me define this for you. And this was, remember, the sum of xi, yi minus the sum of xi times the sum of yi, and that's divided by n. And this is divided by a square root. Okay, this was the sum of xi square minus the sum of xi square divided by n, and this is also multiplied by the sum of yi square minus the sum of yi square divided by n. Okay, in this case, let's substitute all this result within this formula, the Spearman rank correlation, or the Pearson correlation coefficient. Okay, the sum of xi and yi, which is 199, minus the sum of x is 36 times 36 divided by 8, and within the square root, okay, we have the sum of xi square, which is 2.204, sorry, 204. The sum of x is 36 square divided by 8. 204 minus 36 square divided by 8. The result is, if you get this calculation done, and you should get 0.88 and 1. Okay, this is the way you calculate the correlation coefficient, is using the Pearson correlation coefficient formula. But the data set is not continuous, it's ranking. You may say what the point is to use the same formula. The point is, if there is no ties in the data set in the ranking, you may use another formula which is much easier for the calculation. And the other formula, if there is no ties in the rankings, you may use the following formula. So the following formula is R the Spearman equals 1 minus 6 times the sum of the I square divided by n times n square minus 1. That's the formula. It is less complicated and it takes less time to get the correlation coefficient. If there is no ties, I am expecting to get the correlation coefficient to be 0.88 and 1. So let's see in our case. So the di is the difference. I don't have the di in here. I'm gonna get it for you. So di column, this is the difference ranking. It means 1 minus 2 becomes minus 1. 4 minus 3 becomes 1. And another one in here, we have 0, 1, minus 2, okay, and minus 1 and 1. So the sum of the difference, I don't need the sum. The sum is going to be something else. I'm not interested because I need to have the sum of square of xi, di. The first one is 1. The second is 1, 1, 0, 1, 4, 1, and 1. So the sum of di square becomes 3, 4, 8, 9, and 10. Okay, so if I substitute in here, everything is perfectly fine to get the calculation. 1 minus 6 times 10 square divided by 8 times 8 square minus 1. Okay, let me get it. 1 minus 6 times, so it's 10 squared becomes 100, and this is divided by 64 times 63. And I made a mistake. 1 minus 6. This is not a square. I made a mistake in here. So I don't have a square here. 6 times 10. Sixty-three times 64. I have no idea why I'm not getting the same result, but I'm expecting to get the same result. The I is the difference. Square is 10, 60. I made a mistake here. Okay, no Y. Okay, all right. Yes, exactly. I'm getting the same result, which is 0.881. If there is a tie, you cannot use this formula. This one. This formula is not used for ties in the data, ties in the ranking. So the practical formula, is only valid for no ties ranking. So in this case, if you have ties, you use the Pearson correlation formula. Okay. Okay. Let me try to find an example from a book. I might study this example in the previous lecture. Let me see. Example. Have an example. Southern Power is interested in determining the relationship between the square footage of a home and average monthly expenditure for electricity. A random sample of 12 a random sample of 12 homes was obtained. The result of which are shown in the following table. Okay, what is the value of Pearson correlation and the Spearman rank correlation? Okay. The data set home number okay 1 2 let me wait a bit to the okay 2 3 4 5 6 7 8 9 10 11 and 12. X is home square footage. Xi is home square footage. Okay. 17, 24, 17, 11, 19, 28, 35, 13, 23, 15, 29 and 38. Okay. And yeah. And the average electricity bill for Y, $100. The electricity bill. in $100, eh? Okay. YI is given to be 2.1, 1.8. So it means you multiply 1.8 by 100. That is $180 a month. 1.8, 1.5, 4.5, 1.1, 3.0, 2.0, 2.0, 2.8, 1.5, 2.2, 3.1. Okay, this is X and Y. If you try to have the ranking, the smallest value will get number 1 for XI. So in this case, 1 will go for 11. 11 is the smallest value. I'm ranking as 1. The second smallest value is number 8, 13. So this is going to be 2. And number 3 is 15 for 15. This is the third smallest value. And we have a tie, the second smallest. The next smallest is 17. We have 2 of them in here, one here and another one here. So you can't give one as 4 and this one to have 4 and this one is 5. It's not fair because they are equal. So what I'm doing is I'm giving to be you average 4 and 5, you give 4.5, and also in here you have 4.5. For when you have a tie, you average the ranking. That's fine. And the sixth value is 19, so I'm gonna have this 6 because 4 and 5 is given. The average of 4 and 5 is given for the first home the first home and the third home, having 17 square footage. Okay, number 6. In number 7 is 23. That's number 7. And the next value for 20, the next smallest, 7, number 8 is 24. This is 8. And number 9 is 28. And number 10 is 29. 11, which is number 7. That's 11. And 12, 38. So that's 12. Okay. Those are the ranking. So if I place the ranking for average electricity rank, simply this is, I did it myself. 5 in here, 3.5, 1, 2, 11, 6.5, 10, 3.5, 9, and 12. Okay, within a bracket, just to show that they are ranking. Okay. If you use the ranking, so D will be 4.5 minus 8 becomes minus 3.5, and the next one is 3, 1, 0, 4. I'm gonna be quick a bit. Minus 2, minus 4.5. This is plus. This is minus 4.5. And this one is minus 3. This one is minus 0.5, 1, and null. Yeah. Di square 12.25 9 1 0 16 4 20.25, and I have another one here, 20.25 9 0.25 1 and 0. Okay, the sum of the I square is 93, and the Pearson, so the Spearman correlation is equals 1 minus 6 times 93 divided by 12 times 144 minus 1. Okay. The result is Spearman is, if you work it yourself, you'll find 0.675. Okay, this case, I also have the sum of x equals 269. The sum of yi is 23.6. The cross product is 579.3. Okay, the sum of xi square is 853. The sum of yi square is 52.90, and the Pearson correlation for this example, let's get the Pearson correlation, which is okay, 579.3 minus 269 times 23 23.6 divided by 12 and divided by the square root all right, and 6,853 minus 269 square divided by 12. The sum of yi square is 52.90 minus 23.6 square divided by 12. Okay, the Pearson correlation, if you get it done, you'll get 0.688. So it is different from the Spearman 0.675. The reason we get different result is we have some ties. This is a tie 4.5, and we have also 1, 2, 3, 4 ties, and this is why we cannot get the same result. Okay, I leave it to you to study this example to check whether there is a correlation. The correlation coefficient is greater than 0.65. So this is a homework, whether the correlation coefficient is greater than 0.65. That's the end of the lecture. Fall. I shall send you another video file within some days. Take care of yourself and stay safe home. Bye for now.